Machine learning is booming everywhere these days with the bulk of available data, affordable storage, and computing resources. Many industries and organizations are looking for developing robust machine learning models to analyze vast and complex amount of data. Machine learning enables businesses to more quickly adopt profitable opportunities and avoid potential risks. Introducing machine learning in your business is not just about adding new features, but it is an entirely different architecture that compels us to rethink our conceptualization, design, and development. Developing a machine learning system is very different from traditional software development. When you decide to solve problems through machine learning, it is important to prepare your mind and adopt ML mindset. Let's discuss what actually is ML mindset and how it is different from traditional mindset. So there is always uncertainty. Will you end up with a great model as you have expected? Well, you never know for sure. In traditional software development, you have defined parameters and functions, while in machine learning development, also called Software 2.0, you will be doing a lot of experiments and non coding work. In traditional software development, requirements lead towards the final solution, while in machine learning, experimentation is an important step to find an optimized solution for your problem. You should be able to fast fail and move on to the next experiment. In traditional programming, poor quality is usually fixed by removing bugs, while in machine learning, poor quality is not always because of a bug. Machine learning models encode knowledge and intelligence by interpreting data differently than how humans do. For example, a neural network understands words and objects via numeric embeddings. A cat is understood as 0.0003 maybe. These embeddings are then used by neural networks for predictions and translations. If a human tries to find the root cause of bad quality, he cannot possibly explore the embeddings himself. So, debugging of ML models is relatively harder. We do explore a lot of options here, ranging from features, hyperparameters to finding errors in the data. Sometimes, when a suitable ML model is found through experimentation and is ready to be used in production, the interactions can be unpredictable and complicated, making it hard to test all the possible situations. Machine learning teams spend a lot of time figuring out the model behavior in production, and it is a continuous process to improve the models time to time with changing conditions. In 2016, Microsoft released a Twitter chatbot called Tay, which started out as a cool teenage girl. It took less than 24 hours for Twitter to convert the cool girl into an abusive one, so Microsoft had to permanently take down the chatbot. All of the above discussion concludes that machine learning requires a scientific approach towards problem solving, and you need to think like a scientist. So, what is the scientific method? Basically, you will collect information, you will observe the situation and ask questions from experts, then formulate a hypothesis, then design an experiment to test the hypothesis. The observed results are compared with expected results, and then we draw a conclusion that the experiment is good or bad. If the experiment is good, it can lead towards more new experiments, and then we can evaluate different experiments altogether and find the most optimized one. Now let's take a look at machine learning specific project lifecycle. The machine learning lifecycle is very important for a smooth and less bumpy project development because it involves almost all sections of an organization. It takes each and every project from inception to completion and gives a high level perspective of how an entire machine learning project should be structured in order to result in real practical business value. Failing to accurately execute on any one of these steps will result in misleading insights or models with no practical value. The machine learning project lifecycle has four phases: machine learning problem framing, technical feasibility, minimal viable model, then production and scaling. The most important step is to understand the problem and to know the purpose of the problem. So, first of all, we define the business use case. What we can do is we can select top 3 business problems and then we can take one of them and start working on that. After knowing the problem well enough, we evaluate if we have enough relevant data for the problem. Then we select the algorithm which we think will work. Obviously, we cannot experiment all the algorithms. It will take a lot of time. So we will take a look at state of the art work. We can take a look at research papers. We can take a look at other industry standards and shortlist some algorithms. Then we can experiment and choose the optimized one later. Once the algorithm is selected, we will explore the available data, find the most useful features and their representations, and then train our model with that data. Results are evaluated, and if the results are satisfying, the plan for deployment is made. After the deployment, the model is continuously monitored and improved according to the new situations. In this course, we will only focus on business use cases, data exploration, and the factors that impact algorithm selection. Before going towards actual problem framing, let's take a look at types of machine learning and their applications. So, most common type of machine learning is supervised learning. Supervised learning is learning from the past. You need to have a lot of past training data labeled. For example, if you want to classify whether a call is fraud or not, you will construct a dataset which has some features describing the call and a label based on those features saying it's fraud or not. And the model will be trained with this data. We usually keep a chunk of data separate to test the model after training. This way, we can directly know how well our model is performing. And if the performance is good enough, it is ready to be used in real time. Other examples of supervised learning can be predicting the score of a game or knowing whether a plant is poisonous. Next, most common type of machine learning is unsupervised learning. Unsupervised learning helps when labeled past data is not available. So, unsupervised learning will explore the dataset itself. It will deduce the patterns in the dataset, and there is usually no direct feedback process available due to the lack of labeled test data. But we can have an expert to look at the results to evaluate the model. Let's take an example and say your business wants to know more about the customers and you have past information about the purchasing habits of the customers. Now you want to segment the similar customers together. So you can use supervised learning here if you have customer categories defined already and you trust those. But if there are no pre-existing categories available, then you can use unsupervised learning. So the type of machine learning totally depends on your particular scenario. Next up is a different type of machine learning called reinforcement learning. It enables an agent to explore and perform actions in an interactive environment by trial and error method. The agent is actually a machine learning algorithm. The machine learning algorithm is called model in supervised and unsupervised learning, but in reinforcement learning, it's called an agent. So the agent learns and improves according to the environment. It uses feedback in terms of reward from its own actions. A reward is given for positive behavior and punishment for negative behavior. Though it may seem like an unsupervised problem, but the goal is different here. Goal of unsupervised machine learning is to find patterns in the data and group similar points. Maybe. While in reinforcement learning, the goal is to find a series of actions that would increase the cumulative reward of the agent. For example, in a usual autonomous vehicle, the goal is to put safety first, reduce pollution, abide by the rules of law, and offer comfort to the passengers with smooth driving. On the other hand, an autonomous race car should emphasize more on the speed than comfort. The programmer cannot possibly predict all the scenarios on the road by using lengthy if else instructions. So, preferably, the programmer will prepare an agent which learns through rewards and punishments. Let's continue towards subtypes of machine learning problems. Most common subtype is classification. It is a subtype of supervised learning. You must have heard of it many times. In classification, we predict target class of a given sample. Classification can be two-class such as customer churn or multi-class such as identifying from a set of 10 fruits. Next up, we have clustering. So clustering is a subtype of unsupervised learning. Clustering means grouping of the data based on their similarities, or maybe separation of data points based on their differences. It's kind of classification when classes are not known. For example, customer segmentation we discussed earlier. Another subtype of machine learning problems is rule based learning. This type of machine learning identifies and learns rules. Though it's a type of rule based system, it is different from traditional rule based systems as it applies some form of learning to automatically deduce rules rather than handcrafted rules. Most common type of rule based learning is association rule learning, and the most common application of association rule learning is product shelving. For example, in a supermarket, what should be arrangements of products on the shelf? So, rule based learning can tell us if the customer buys bread, he is likely to buy the milk. Now we have regression. Regression is another subtype of supervised learning. Regression means predict continuous values, such as housing prices forecasting. Another machine learning subtype is anomaly detection. Anomaly detection is about finding the rare, abnormal, or unexpected points in the data. It is also called outlier detection. It is most commonly used to detect fraud in credit card transactions. Next up is structured output. So, when prediction of supervised learning is not a scalar or a numeric value, it's called structured output, such as recognizing objects in an image and drawing bounding boxes around them. Moving forward, how can you know that your selected problem is good to be solved through machine learning? Well, it should have following attributes. Number one, there is a pattern to identify. So, know your problem well enough. Machine learning at its core is a set of methods to find patterns of the predictability in datasets. These methods are great at deducing how certain features impact the outcome, but they cannot access any knowledge outside of provided data. Next, you should see if the problem is complex enough and it cannot be solved mathematically. So, focus on a problem that cannot be solved with traditional programming. Machine learning is not about simple automation. And remember that your focus is to solve a problem, not just use machine learning as a hammer to everything. Check that if your problem requires predictions and then decisions. So, you want to use machine learning to find out how certain aspects of the data relate to each other. Machine learning does not bring intuition or domain knowledge, and your system should take actions on the basis of predictions. If it only requires insights from the data, machine learning is not suited. Sometimes predictions and decisions are aligned, sometimes they are not. For example, you want to predict what product user wants to buy next, then take a decision to show that product in recommended products. Verify that you have enough samples of data to learn about the problem, and it will be most useful if you have data specifically collected for your task. In practice, it may not be the case, so you will rely on whatever data you have that's close enough. Just be aware of the cost. You can eventually get more relevant data to improve the model. Now the question arises, how much data is enough? So that depends on the scenario. But the more, the better. Consider hundreds or thousands of samples to start with machine learning. If it's not possible, go with non-ML solution first. Last but not the least, check that the task is sufficiently self-contained and you are relatively certain that the data you feed to your learning algorithm includes more or less all there is to the problem. If in the future things change unexpectedly and it no longer matches the prior patterns, the algorithm will not be able to adopt the change. And these methods cannot access any knowledge outside of the data you provide. For example, researchers at the University of Pittsburgh in the late 1990s evaluated machine learning models for predicting mortality rates from pneumonia. The algorithms recommended that hospitals sent home pneumonia patients who were also asthma sufferers, estimating their risk of death from pneumonia to be lower. Later, it turned out that the dataset fed into the algorithms did not consider the fact that asthma sufferers had been immediately sent to ICU and they had been better only due to the additional attention. Many believe we are living in the prime age of machine learning, but there are still some challenges and hurdles that need to be solved by the researchers. For now, let's discuss what kind of problems are hard to be solved by machine learning, and if your business problem lies in these areas, you should rethink using machine learning. Most challenging problem in machine learning is describing contents of a cluster. Now, if you have unlabeled data and you apply clustering, it will provide you groupings of similar items. But if you want to describe the groupings and tell why certain items are in a group and what is actually that group, it is definitely hard for machine learning. So, machine learning can provide clusters, but it cannot explain the cluster details. Another challenging problem in machine learning is anomaly detection. Since anomaly detection is all about finding unexpected points in the data, which happens to be rare, their past examples are also very rare. And we know that machine learning tries to learn from the past. So it's hard to find the anomalies and you may have to set some threshold. ML cannot help if training data does not spot the problem solution. We already know machine learning finds patterns in existing data. If data you provide is too random or there are no clear patterns, machine learning will not be able to solve the problem. You have to change the data and add meaningful features to introduce patterns. Machine learning can predict according to the task, but it cannot explain why it took that decision. Why certain objects are in a certain class. For instance, an image recognition algorithm that classifies apples and peaches, so it cannot tell why the fruit is peach. In case of unsupervised learning, machine learning can group together similar data points, but it wouldn't tell you why these points are similar and why they are chosen to be in the same group. In short, machine learning algorithms lack reasoning. If your business problem needs explanation of your decision, you may want to consider other alternatives with machine learning. ML cannot help if existing data is not available. If your business problem does not have relevant data, you cannot solve it with machine learning since machines are not magic. If you find data for similar tasks, you can use machine learning, but the correct predictions are not guaranteed. Problems that require emotional intelligence cannot be fully solved through machine learning. Other challenging problems in machine learning includes creating art and game design. Though ML can produce movie scripts and paintings, but it is still an undiscovered field. Machine learning cannot design new games on its own as well. AI and machine learning have proved to be good at playing games just recently, but machine learning is not capable of designing new rules for a new game. Sentence comprehension is another difficult task for machine learning. Do these two sentences say the same thing? Well, for sentences that look very similar or use synonyms, you can tell this reasonably well, so as the machine learning. But beyond that, there is a lot more to do. Particularly, sarcasm detection is very hard. Also, it's very hard for machine learning to understand idioms and metaphors. Video understanding is another challenging problem in machine learning. Given a drama video, identify how the characters are related. Well, humans are very good at this. Relationships like friends are very tricky to infer for the machines because most of the time they don't explicitly refer to each other as friends. Next, we have zero or one or several short learning. So, humans, animals, and insects can learn from very little information in a very complex way. Trying to incorporate such capabilities in machines has remained a challenging task. Problems such as handwriting recognition with few samples are still very hard. Machine learning is data hungry, though sometimes we can reuse models trained on a dataset to predict other similar data points, but it does not help everywhere. Generalization is another challenging task in machine learning. ML can only help solve a task if past examples have been used for training. If a new test case, very different from training samples, occurs, machine learning will fail. Once we know the characteristics of good and bad ML problems, it's time to select our own specific business problems. So, what should be the criteria of business use case selection? Choose a problem that allows some margin of error. Machine learning solutions will be incorrect for a certain percentage of the time, especially when a different test case occurs. And if your use case does not allow any error, machine learning should not be used. For example, you want machine learning to read the amount on a bill and then pay it. One slight difference can cause overpaying your bills by multiple factors. But if you just want to group together the similar amount invoices, machine learning is good to go. So you should choose a priority problem. Do not go for machine learning for the sake of using machine learning. Pick a problem that matters a lot and have higher likelihood of being solved. Example areas where machine learning can help are personalized learning, personalized marketing, risk and fraud analysis, predictive equipment maintenance, and many more. So you should clearly understand the problem and then start simple and clear. For example, you can say, we want the machine learning model to predict if a given person is in the photo. After that, you should clearly define your goal. What should machine learning do for you? What is the larger objective of using machine learning? Remember, ideal outcome is different from machine learning model evaluation techniques such as area under the curve or accuracy. For example, you can say our ideal outcome is to quickly find a given person in a given photo so that all related data is loaded and the person can be authenticated easily. Success and failure metrics. Now it's time to define a quantifiable outcome, and you should have success and failure matrices set before you go ahead with machine learning. For example, success means 95% of the time the system was able to identify the person in the photos correctly. You should also define failure criteria here. Failure means 40% of the time the system identified the wrong person in the photo. Once you are done with success and failure matrices, there are few more questions to be asked. First one, is the success metric measurable? So can you measure the number of times the system was able to identify the person in the photo correctly? And how will you measure the success of your machine learning solution? So you can do A/B testing here. You can use 3 control groups: random, business as is, and then model based. For example, you want to identify users who might churn, so companies will offer them some incentives so they do not leave. And you have trained the model. Now, how are you going to measure its value? What you can do is randomly select 100 users from all available users and count how many actually churned. Then you can also select 100 customers or users based on the rules defined by marketing team, and that is as is situation. You can also select 100 customers or users using AI model you just trained. Then you can compare the accuracy of all the 3 methods and calculate the difference. If machine learning is performing better than the business as is situation, then you can definitely say that machine learning is working for you. Another question arises that when can you measure it? When will you have enough data to measure it? So you should test your minimal viable product in real world before productionization. You should also consider other failure scenarios which are unrelatable, such as what if your system was able to correctly identify the person in the photos 95% of the times, but the output was too slow. Another question is, how long will it take to know if the system is success or failure? Ideally, you should know it as early as possible so you can avoid big changes and the cost. Next, and an important step is to analyze machine learning objective. You need to carefully consider the machine learning objective of your system. Wrong objectives often lead to undesired outcomes. So consider the example of a book recommendation system. One objective can be maximizing the click rate. What if the book is clicked but no one actually reads it? So another objective can be maximizing the read time. If that's the case, system will recommend longer books on the website. Some users will read it, but most of the users will quit altogether. Consider another example of increasing revenue from sale. So, one objective can be to increase sale by increasing average basket size. Machine learning will recommend similar bought items within the buyer's pocket, such as suggesting vegetables with fruits. Another objective can be increase sale by selling expensive items. So this time, machine learning will recommend expensive items to customers. They may buy it sometimes, but the long-term revenue and the relationship cannot be retained. Discover how a good output can be designed for a business problem. Let's quickly take a look at types of machine learning models by output and see what kind of output is needed in your case: numeric, cluster, category, or something else. Sometimes, machine learning problems that fail with one output type can succeed with another type of the model. So, if your problem has to do something about picking up a label from a defined set of labels, then you are going for classification. For example, if the comment is positive, negative, or neutral. If your problem is about something complex, such as recognizing the objects in an image and drawing bounding boxes around them if you want to translate from one language to another, or if you want to summarize a long text, then you are going for a structured output type of model. Regression will be used if you have to predict continuous numeric values such as housing prices, currency rates. And if you want to group similar objects, images, or words together, then you can use clustering. Rule-based learning models will be used if you have to infer association patterns. This kind of machine learning is useful in marketplace analysis, medical diagnosis, and protein sequencing. You must choose a good output for your machine learning model, as the whole training and deployment process will heavily depend on it. So first of all, your output should be clearly defined. For example, in case of classification, you should have a set of categories to predict from. And your output should be quantifiable so machine can produce it. For example, in the case of predicting whether a user liked the app, you cannot tell without asking the user. Now, if you cannot ask the user, then you can use some alternate metrics or labels to measure that. Such as, if the user spent more time on the app related to other apps, he may like it. But there is a problem. Sometimes user will spend more time on the app if it's causing an issue as well. But you can still go for it, at least it's quantifiable. Your output should be connected to the ideal outcome. Even if you had to use an alternate label, it should be connected to your true outcome. For example, if your outcome is to show more products to encourage the customer to buy more stuff, then your output can be to predict whether customers buy product B with product A. Now you have an important question to ask. Do you have example outputs for your training data as well? You may need to engineer the output examples, but if it is too difficult to obtain the output examples for your training data, then you should reconsider the output type for your problem. Since the goal of predicting from machine learning is to use it in decision making, the output usage also matters. How will you use the output of the machine learning solution? Online, in case of real-time predictions and taking decisions instantly, and offline in case of batch prediction, then taking decisions altogether. This is the time to figure out how you will make a decision after the prediction. This is the time to also figure out what kind of data will be available at the time of prediction so that you can use only those features to train the model. Also consider the latency at this stage. How crucial is the timing in online prediction? Let's begin to frame any problem into a machine learning problem. We have further divided machine learning model types here. So this is a flowchart to pick a certain type of classification for your own problem. Most basic type of classification is binary classification, when the number of categories to pick from are equal to 2. Such as in the case you have to identify if there is an animal in the video or not. or if there is an apple in the image or not. These kind of classifications are called binary classification. But if number of categories are more than 2, that's called multi-class classification. If you have a problem such as an image containing multiple objects and you want to know all of their names, so that's a multi-class classification problem. Now, in multi-class classification, there are further two types, which depends on the number of categories for a single example. If your single example can contain only one label, that's called multi-class single label. For example, you have number of categories defined as apple, oranges, peaches, and bananas, and now you want to predict from an image if it contains any one of these categories. And at a time, you have to predict only one fruit, such as you can say for an image, you can predict it's an apple. For an image, you can predict it's a peach. So that's called multi-class single label classification. But if there are many fruits in the image and you have to predict all of these, such as you can say there is an apple and peach and banana in the image, then that's called multi-class multi-label classification. So you need to check which classification type you need in your particular case. Again, in case of regression, there are two types of regression. First one is unidimensional regression. So if you want to predict only one variable, such as minutes of the video the user watches, it's called unidimensional regression. But if you want to predict multiple continuous values, then it's called multidimensional or multivariate regression. Such as you have data on cholesterol, blood pressure, and weight, and you also have the data on the eating habits of your subjects, such as how many ounces of dairy products and chocolate and fish and wheat they consumed per week. Now you want to identify the relationship among eating habits and these three target variables. That's a perfect example of multidimensional regression. Moving on towards the formulation of machine learning question, first of all, we need to identify model prediction. So, what will our model predict? For example, our model will predict animal class from the image. Now, next step is to formulate your problem statement. Formulation of problem statement always makes your process easier. So, combining the above in a single problem statement, we can say that our problem is best framed as 7-class multi-label classification, which predicts one of 7 classes: horse, goat, cow, cat, dog, donkey, and deer. The next step is to simplify the problem. If you are using multi-class classification, then you should simplify it to binary classification, such as predicting 7 animal classes from the images to predicting if there is an animal or not. If you are using multi-dimensional regression model, then you can convert it to unidimensional regression model, such as if you have to predict sale of multiple products, then you can start by predicting sale of a single product. So why simplification is important? At this stage, we want to determine whether machine learning is useful for the business or not. So we cannot afford the machine learning system to fail after spending a lot of money and time. Machine learning model objective may not directly correspond to your business objective, and you can only know it by the experiments. So your experiments need to be simple and quick to know. So you should focus on simple architectures and perfect the dataset. It's better to run a simpler model and improve it over time instead of running a complex pipeline on unsuitable data. Studies have shown that the biggest gain in business achieved by machine learning is shown in the initial stages, and it slowly improves through later experimentation. So we get to know at this stage if machine learning is increasing our business value. Next, we should find a suitable heuristic technique that would work in the similar scenario without machine learning. You need to think, how will you solve your problem without machine learning? With heuristic techniques, we can experiment and compare if machine learning actually helps in solving the problem. If it does, we can always improve the system. If the heuristics are better than machine learning solution, we may need to change the strategy of solving the problem with machine learning, or maybe we do not need machine learning in that particular case. We have formulated ML question and decided the model type. Now it's time to focus on the data sources, and data preparation cost. In order to identify relevant data sets, do you have enough clean new data to train the ML model? Obviously, you should have enough data to train the machine learning model, since machine learning has to learn from the past examples. Clean data is better than big data is a common phrase. If you have a lot of business data from years ago, it may have no relevance today, particularly in fields where the business processes change drastically year over year, such as mobile e-commerce. If you have lots of unstructured and disjointed data, you may have too much cleaning to do before you can ever get around to learning from the information collected. Does the available data actually help in decision making? Your data should be directly related to machine learning model output, which in turn makes it related to your ideal outcome and decision making process. Is the data labeled? While unsupervised machine learning allows it to make sense from unlabeled data for a wide range of applications, it's usually not advised for businesses to jump into machine learning with a first application in unsupervised learning. So you should think about labeling your data. How close is the data to the real scenario? Sometimes collected data is irrelevant and may help in other tasks, but it does not represent the real scenario properly, or it may not have enough examples to consider the wide variety of range from the real scenario. If that's the case, consider recollecting the data that's close enough and captures everything. Is granularity in training and testing the same? Granularity means the details in the data stored. What if you want to forecast the user's next action on the basis of previous 5 actions, and you have trained your model according to that data? What if at the time of testing and at the time of real prediction, you do not have set of 5 previous actions, instead you only have 3? For example, you can answer all those questions by a statement saying, we have past examples of 10,000 reviews of our 5 products, labeling the product as popular, somewhat popular, and not popular. This will summarize your data sources. Once you have the data that supports the decision-making process, identify the inputs and outputs to the machine learning model. You may have to denormalize data by combining multiple sources. While preparing the data according to machine learning model, each row represents one sample of the data. Only use the inputs that will be available at the time of testing. And each input can be scalar, such as number or sales record, or string such as product title, or integers and floats. Sometimes we do not have 1D or scalar data. For example, an image classification model will take images as input, and a speech recognition model takes audio as input. An example from a data prepared according to a classification type of machine learning model is shown here. We have 4 features: product launch date as a date type, then we have product title as a string, then we have daily sale as a number, then again we have a date. And the label is a string type. This is the time to consider the cost of fetching the data and preparing it for machine learning modeling. You need to consider how much time will it take to collect the data, how the raw data will be transformed into a proper format to pass the model. You can do it manually or using automated ways. If it's too hard to fetch the data along with the example output, you need to revisit the whole process. You also need to consider if you can afford the cost of building the data pipeline in terms of money, resources, and time. At this stage, you need to also consider, is it possible to label the data? So we already know that we need labeled data for supervised machine learning, and we consider that our training examples should have labeled data. But at this stage, you have defined your data sources, you know how vast your data is. Now, is it possible to label the data in terms of money, resources, and time? In the data assessment final steps, what you should do is shortlist the inputs. You need to pick the top 1 to 3 easily available inputs from the set of all features. What you can do is use heuristics to pick top inputs, which information has proven to be the most useful in taking the decision in the past. So model will take the input, but all of the context must be taken into account by you. For example, in case of recommending related products, a recommendation engine for an e-commerce retailer over-recommends a specific product. So it was discovered later that the product was promoted heavily over a year ago. So historical data showed a large uptick in sales from existing buyers. However, these promotional purchases were sold more based on the deal and the low price, and the less so by the actual related intent of the customer. We need to evaluate the learning ability of the model and consider the potential biases before proceeding towards actual machine learning model training. What prevents models from learning? So your machine learning model will not learn if the dataset does not contain enough positive labels. For example, in multi-class classification, there should be almost equal representation of all classes, otherwise models will not be trained efficiently. Another reason which prevents models from learning is not having enough examples in the training dataset. So the model will not learn if the dataset is not capturing enough varying diversified examples. For example, digit 6 always varies in handwriting. And the model will also not learn if the dataset is noisy. Noisy means the labels are not true sometimes. This can be avoided by manual checking or automated checking of ground truth. Overfitting or memorization of training data is another cause of bad learning of machine learning models. Sometimes when training data is small or covers almost the same type of examples, the model memorizes it and does not fit well to even slightly changed scenarios. This can be overcome by adding more diverse training data. Next reason is old data and false correlations. So the model will fail in real time if training data used was old. The changes in variables and scenarios are unavoidable in the real world. That's why machine learning models need continuous improvement. And if the input and output variables are not actually related, they are just coincidentally related, that's called false correlation. And it will lead to bad learning of the model. Feedback loops is another reason of bad learning of machine learning models. A feedback loop is a situation where an algorithm's decisions affect reality, which in turn convinces the algorithm that its decision is correct. For example, a crime prevention program in California suggested that police should send more officers to African American neighborhoods based on the crime rate. But the crime rate increased due to the more police cars in the neighborhood, which led to officers writing up more reports, which resulted in a higher crime rate, which meant more officers had to be sent to the area. Every data has some bias in it. Some possible biases are discussed. Exclusion bias. So exclusion bias is most common at the data pre-processing stage. Most often, when selecting top features, engineers delete valuable data thought to be unimportant. For example, imagine you have a dataset of customer sales in America and Canada, and 90% of the customers are from America, so you choose to delete the location thinking that it's irrelevant. However, this means that your model will not pick up on the fact that your Canadian customers spent a lot more than your American customers. Another bias is underrepresentation, and it is one of the most common causes of bias in machine learning algorithms. Underrepresentation means that training data is missing samples for underrepresented groups or categories. This is the reason why voice control systems such as Siri frequently have a hard time understanding people with accents. Another bias is experimenter's bias. Sometimes an experimenter keeps on training the models until a pre existing hypothesis is proved. Then there is group attribution bias. This type of bias results from when you train a model with data that contains an asymmetric view of a certain group. For example, in a certain sample dataset, if the majority of a certain gender would be more successful than the other, or if the majority of a certain race is involved in more crimes, your model will be inclined to believe these falsehoods. There is label bias in these cases. In actuality, these sort of labels should not make into a model in the first place. This kind of data should be anonymous. The sample used to understand and analyze the current situation cannot just be used as training data without appropriate engineering or removing personal information. Selection bias. Selection of samples from a pool of data often causes bias, and it includes sampling bias and coverage bias. Sampling bias means the selected sample group is not random, and the coverage bias means the selected sample group does not match with the group that machine learning model is predicting about. For example, so you want your machine learning model to predict if people enjoyed a particular movie. And to collect training data, you have handed out a survey form to front row seaters, as that would be the easiest way, but it may include coverage bias. Again, many facial recognition systems are trained primarily on images of white men. These models have considerably lower levels of accuracy with women and people of different ethnicities. The prevention of bias in machine learning projects is a continuous task. But there are a number of steps that can help prevent bias in early stages. So, be aware of your general use cases and potential outliers. Hire a diverse team of engineers and data labelers. Take input from multiple sources wherever possible. This can also prevent the bias. You can create a gold standard for your data labeling. A gold standard is a set of data that reflects the ideal labeled data for your task. It enables you to measure your team's annotations for accuracy. Then you can get in touch with domain experts to review your collected or annotated data. Someone from outside of your team may see the biases that your team may have overlooked. Analyze your data regularly. Keep track of errors and problem areas so you can respond to and resolve them quickly. Also, carefully analyze data points before making the decision to delete or keep them. And you should include bias testing in the development phase as well. AWS and other cloud services offer a lot of tools and guides to help with analyzing bias for a number of different data types. There are various machine learning algorithms that can be applied to a given problem. For example, a spam comment detection problem can be solved through logistic regression, naive Bayes, and deep learning techniques as well. It is crucial to decide which model to implement from a wide range of models. Though we can evaluate models using accuracy, recall, or precision, but it's not wise to train them all. So it's important to know how to select the right algorithm for your particular problem. Let's discuss factors that impact algorithm selection. Size of training data. It is useless to train a complex and large model on a small data. If the size of training data is not large enough, use high bias and low variance models such as SVM or naive Bayes. Number of features also impact algorithm selection. If you have a small number of features, you can choose simpler and smaller models. But for a large number of features, you may need to use machine learning approaches to select top features. Data storage capacity is another factor that impacts algorithm selection. At the time of training, If your data can be fully loaded into RAM, you can apply a wide range of algorithms. But if that's not possible, you may need to adopt incremental learning algorithms. And if your data storage capacity is low, you cannot store gigabytes of a complex machine learning model, such as embedded systems have low capacity. Data format also impact algorithm selection. Algorithms can only work with numerical data, so if your data is categorical or otherwise non-numerical in format, then you will need to consider a process to convert it into numerical data. Another factor that impacts algorithm selection is linearity of the data. Identifying the linearity of data helps to determine the shape of the decision boundary, which in turn guides us to the machine learning models we can use. If the data seems almost linearly separable, algorithms like linear regression (SVM) are a good choice. Otherwise, deep learning or ensemble methods work better for nonlinear data. Another factor that impacts algorithm selection is prediction time. Real-time applications require very fast prediction. For instance, in autonomous car driving, it is important to classify road signs and traffic signals as soon as possible. In these cases, because speed is so important, even an algorithm with good results isn't useful if it is too slow at making predictions. However, it's worth noting that there are business requirements where accuracy is more important than prediction time. This is true in cases such as detecting fraudulent transactions. Learning time. It is the time taken by an algorithm to train and create a model. Sometimes models need to be trained once, such as medical diagnosis, but sometimes training is required every second like stock predictions. So considering the time taken to train the model is essential. Maintainability. Always choose a model that's easier to maintain in the future for your problem. A very sophisticated solution may give slightly better results, but it will not be easy to update the solution to fix a bug in the future. Interpretability. Choose a relatively simple machine learning model if explainability is a key consideration. Now let's take a look at this cheat sheet that helps in choosing the right algorithm for your problem. We will start from the center. If you need dimension reduction, then you can go for unsupervised learning techniques that help in dimension reduction, such as principal component analysis, singular value decomposition, and latent analysis. But if your problem is not about dimension reduction and you have labeled data, it means you can go for supervised learning. So if you have to predict a numeric value, then you should go for regression in supervised learning. And in regression, if speed is more important than accuracy, you can use decision trees or linear regression. And if accuracy is most important thing, then you can go for random forest, neural networks, gradient boosting trees. Now, if your goal is not about predicting a numeric value, instead you have categorical data, then you can go for classification in supervised learning. If accuracy is most important, then you can go for kernel SVMs, random forest, neural network, gradient boosting trees. And if speed is more important and you need to explain your decisions as well, then you can go for decision trees and logistic regression since they are simpler. But if explainability is not required and your data is too large, then you should go for naive Bayes. But if your data is not too large, you can also use linear SVM. Now going back to the second stage, if your dataset is not labeled, then check if it's hierarchical. If yes, then use hierarchical clustering. If no, then check if you have number of clusters defined. If yes, check if your number of clusters are actually a categorical variable, then you can use K-mode's algorithm. If categorical variables are not available, instead it's numeric and you prefer probability, then use Gaussian mixture model. If you do not prefer probability, then you can use K-means algorithm for clustering. And if you do not have to specify number of clusters, then you can use DB-scan algorithm. Remember, this cheat sheet is made from mere opinion of experienced data scientists, machine learning engineers, and using existing state-of-the-art models for particular problems. This is not a hard and fast rule to apply machine learning. Rather, it's for beginners to start machine learning easily. At the end of this course, before moving towards more advanced machine learning, let's refresh few machine learning terms that are focused in the exam as well. How to tell if the generalization is working is an all-present topic throughout the exam. You will need to be able to explain how confusion metrics and other evaluation matrices work. Confusion metrics. Here is an n by n confusion matrix for a binary classification model where n is 2, as the number of target classes in binary classification model is 2. This matrix compares the machine learning predictions with actual target values. Let's imagine our two target classes are positive and negative. Positive means sick and negative means not sick. So, our confusion matrix will provide as TP true positives. True positives will represent the number of samples where machine learning correctly predicted sick people. It also clears our confusion about Tn. Tn meaning true negatives, the number of not sick people machine learning predicted successfully. Then again, there is Fn. Fn meaning false negatives. False negative is the number of samples where machine learning predicted sick as not sick. Then we have false positive, Fp, number of samples where the model predicted not sick people as sick. So this information is very useful for us. We can use it to further calculate more evaluation matrices, and each metric has its own importance. Let's take a look how we can calculate other important values out of this confusion matrix. We have changed the letters to represent TP, Tn, Fp and Fn. Here TP, true positives are represented by A, and then true negatives are represented by D, and then false positive is represented by B and false negative is represented by C. So most important metric which we can calculate from this confusion metric is accuracy. As you can see the formula for accuracy written at the right bottom of the table. Accuracy is the number of true predicted samples divided by the number of all samples. So we can say that we can add true positives and true negatives and divide it by the total number of samples, then we can achieve accuracy from this confusion matrix. Let's say we want to predict how many people are infected with COVID. So we can isolate them from the healthy population. So our two target values will be sick or not sick, and total number of people tested are 165, out of which true positives are 45 and true negatives are 104. So the accuracy in our example is 90%, which is pretty good. Now, we don't want to use accuracy here as our dataset is not balanced. It is important for us to know how many sick people were identified as not sick and they could not be isolated. For that, we need another measure called recall. Recall is the number of true positives divided by the number of actual positives. So here the recall is 0.75, which means it is identifying sick person correctly only 75% of the time. Recall is important in medical cases where it doesn't matter whether we raise a false alarm, but the actual positive cases matter. When false positives are of higher concern over false negatives, we use precision to evaluate the model. It is useful in problems such as e-commerce or recommendation systems. Precision is the number of true positives divided by total number of predicted positives. So the difference between precision and recall is that precision is measuring what fraction of your predictions for the positive class are valid, while recall is telling you how often your predictions actually capture the positive class. The goal of a good machine learning model is to get the right balance of precision and recall by trying to maximize the number of true positives while minimizing the number of false negatives and false positives. F1 score takes into consideration both precision and recall. F1 is usually more useful than accuracy, especially if you have an uneven class distribution. So basically, a classifier with a precision of 1 and a recall of 0 has a simple accuracy of 0.5, but an F1 score of 0. So F1 score can be calculated by multiplying precision and recall, and then dividing it by precision plus recall, then multiplying the answer with 2. Next, we have an ROC curve. So ROC curve plots the true positive rate on the y-axis versus the false positive rate on the x-axis. The true positive rate is the recall and the false positive rate is the probability of a false alarm. And both of these can also be calculated from the confusion matrix. Next topic we are going to refresh is hyperparameter tuning. So hyperparameters are the values that control the learning process of a machine learning model. And the performance of a machine learning model depends on the right selection of the hyperparameters. So we need to choose the optimal set of parameters for efficient learning. This process of trying and choosing the best one out is called hyperparameter tuning. Traditional machine learning versus transfer machine learning. These are types of machine learning by task. So traditional machine learning works by learning isolated single tasks, and knowledge is not retained or accumulated, and the learning is performed without considering past learned knowledge in other tasks. While in transfer learning, the learning of new tasks relies on previous learned tasks. Transfer learning is an emerging field in machine learning where we want to reuse our trained models and available datasets for new tasks. In transfer learning process can be faster, more accurate, and it needs less training time and data because it's sharing the knowledge between two tasks. Overfitting and underfitting. So a machine learning model is called best fit on its data if the error in training and testing is almost the same. But the model is called underfitting or high biased, low variance if the error is high on both testing and training data. But if testing error is far higher than training error, the model seems to be overfit or high bias and high variance. If you face these issues in your model, there are a number of strategies you can employ. For instances of high bias in your machine learning model, you can try increasing the number of input features. Plotting model error as a function of the number of input features you are using, we can find that more features leads to a better fit in the model. And it follows then in the opposite scenario of high variance, then you can reduce the number of input features. If your model is overfit to the training data, it's possible that you have used too many features, and you should reduce the number of inputs to make your model more flexible to test datasets. Similarly, sometimes increasing the number of training examples can also help cope with overfitting and make the model more generalizable. So, in this course, we have analyzed the problem framing in machine learning and choosing the right algorithm while refreshing some basic ML concepts. You have learned the importance of the ML mindset and how it is different from traditional software development. You revised common types of machine learning along with their examples. You also examined the steps that should be followed while formulating machine learning problems and how to evaluate the learning ability of your solution. You also refreshed some core ML concepts such as evaluation metrics, hyperparameter tuning, overfitting, underfitting, and transfer learning. Coming up next, we have machine learning with SageMaker to get our hands on solving problems practically.